The winter morning brought a pale, cold light to the Kummersdorf testing facility, one of Germany's most important military research and development complexes. Located in the pine forests south of Berlin, the sprawling installation housed proving grounds, ballistics ranges, and technical evaluation workshops where captured enemy equipment underwent rigorous analysis. On this particular morning, the temperature hovered around -3 degrees Celsius, and a thin layer of frost covered the evergreen branches surrounding the facility's main entrance. Early in the morning, a heavy Büssing-Nag transport truck bearing Wehrmacht markings rumbled through the security checkpoint, its diesel engine laboring under the weight of its cargo. Behind the wheel, the driver navigated carefully along the facility's main access road, following directional signs toward the armored vehicle testing section. In the passenger seat, Hauptmann Werner Vogel, the facility's technical liaison officer, reviewed paperwork detailing the morning's delivery. One captured American M4 Sherman medium tank, recovered from the Anzio beachhead in Italy 3 weeks prior, transported by rail through Austria and Bavaria, now designated for comprehensive technical evaluation. The truck proceeded past administrative buildings and barracks, eventually reaching a large concrete apron surrounded by several massive steel-framed workshop structures. Here, the facility maintained specialized equipment for handling armored vehicles, heavy gantry cranes, welding stations, and precision measurement tools necessary for detailed analysis of enemy tank designs. Waiting near Workshop 3 stood Oberstleutnant Dr. Heinrich Keller, the facility's senior armor evaluation specialist and a man whose career in tank design stretched back to the early 1930s. At 51 years old, Keller represented the pinnacle of German armored vehicle engineering, educated at the Technical University of Berlin, veteran of numerous panzer development projects, holder of patents related to armor plate manufacturing and turret traverse mechanisms. Beside him stood 3 additional engineers: Hauptmann Ernst Zimmermann, a 38-year-old specialist in automotive powertrains and transmission systems; Major Klaus Reinhardt, a metallurgist focused on armor composition and protective technologies; and Oberleutnant Franz Bauer, a young but brilliant mechanical engineer who had worked on the Tiger tank development program. This team represented considerable expertise, assembled specifically to conduct what military leadership hoped would be a thorough and revealing analysis of American tank design and manufacturing capabilities. The transport truck's hydraulic lift whined as its flatbed tilted, and slowly, carefully, the Sherman tank rolled backward down heavy steel ramps onto the concrete apron. The tank moved under its own power, driven by a Wehrmacht panzer crew member who had been trained to operate captured equipment. The rumble of the Sherman's radial engine echoed off the workshop buildings, its distinctive sound different from the higher-pitched whine of German Maybach engines. As the tank cleared the ramps and settled onto the concrete, the driver shut down the engine, and sudden silence filled the cold morning air. The Sherman sat motionless, an artifact of enemy industrial capacity, now subject to German technical scrutiny. The tank measured approximately 6 meters in length, 3 meters in width, and stood nearly 3 meters tall to the top of its turret. Its hull construction immediately struck the observing engineers as distinctive. Unlike German tanks, with their interlocking armor plates and complex joinery, this American vehicle featured large, simply shaped armor sections joined by continuous welded seams. The turret, particularly notable, appeared to be a single cast steel piece, its rounded contours lacking the angular precision of German turret designs. The entire vehicle was painted in a flat olive drab color, now weathered and chipped from combat operations. Mud caked the tracks and suspension components, and several areas showed impact marks where projectiles had struck without penetrating, testimony to recent combat experience. Dr. Keller circled the tank slowly, his trained eyes cataloging details. The Sherman's profile was noticeably taller than comparable German medium tanks, presenting what he immediately recognized as a larger target silhouette. Its main armament, a 75mm gun, protruded from the cast turret. Adequate firepower, but nothing exceptional by German standards, where 75mm guns were considered standard for medium tanks and larger calibers, increasingly common for heavy vehicles. The suspension system visible beneath the hull consisted of vertical volute springs, a design the Germans had largely abandoned in favor of torsion bar, suspensions that provided better performance and simplified hull construction. Everything about the Sherman's external appearance suggested a design philosophy fundamentally different from German approaches, though the full implications of these differences would only become apparent through detailed analysis. Workshop 3's interior could accommodate 3 tanks simultaneously, with overhead gantry cranes capable of lifting complete vehicles or removing major components. The space was heated by a large industrial furnace system, though the massive volume meant temperatures rarely rose above 10 degrees Celsius during winter months. High-intensity work lights hung from the ceiling, supplementing natural light from skylights and tall windows. The concrete floor showed oil stains and track marks from countless vehicles that had passed through for evaluation or repair. Along the walls, extensive tool storage systems held specialized equipment, torque wrenches, precision measuring instruments, cutting tools, and welding apparatus. Her separate glassed-in office space in one corner housed drawing tables and technical reference libraries. The Sherman had been positioned in the central bay, with the engineering team now conducting their preliminary external examination. Hauptmann Vogel had distributed clipboards with standardized evaluation forms, and each engineer began documenting observations in their area of expertise. Major Reinhardt focused on armor construction, running his hands along welded seams and examining the cast turret's surface finish. He produced a small geology hammer and tapped various armor sections, listening to the acoustic response and making notes about probable plate thickness and composition. Hauptmann Zimmermann crawled beneath the tank, examining the suspension, drivetrain, and hull underside. His muffled voice provided commentary to Oberleutnant Bauer, who transcribed observations while simultaneously photographing the undercarriage using the facility's precision camera equipment. Dr. Keller, meanwhile, had climbed atop the Sherman, opening hatches and examining the turret's interior configuration. The smell of oil, gunpowder residue, and the distinctive odor of American military equipment, a combination of specific lubricants and materials, filled his nostrils as he peered into the crew compartment. What immediately struck him was the spaciousness compared to German tank interiors. The Sherman's turret provided considerably more internal volume than comparable German designs, allowing easier crew movement and reducing the claustrophobic conditions that plagued many Panzer crews during extended operations. The afternoon session brought more detailed examination as the team compiled their initial findings. A pot of ersatz coffee sat on a workbench, providing minimal warmth and dubious refreshment as the engineers gathered to compare observations. Dr. Keller had prepared a large chalkboard where he began organizing their discoveries into categories: armor protection, firepower, mobility, crew accommodation, and manufacturing characteristics. The discussion quickly revealed a pattern of observations that challenged some preconceptions while confirming others. Major Reinhardt reported his armor analysis findings. The Sherman's frontal hull armor measured approximately 51 millimeters thick, angled at 56 degrees from vertical, reasonable protection, but inferior to the frontal armor of German Panther tanks, which featured 80 millimeters at similar angles. The turret's cast construction, while innovative, resulted in armor effectiveness roughly equivalent to 75 millimeters of rolled homogeneous armor plate. By German standards, this protection was adequate but not exceptional. However, Reinhardt noted something significant. The welded construction showed remarkably consistent quality. Every seam he examined displayed uniform penetration, proper heat treatment, and minimal defects. German tanks often featured superior individual armor plates, but welding quality could vary significantly depending on which facility performed the work and the skill level of individual welders. This American tank suggested highly standardized welding procedures and possibly automated or semi-automated welding processes that produced consistent results regardless of individual worker variation. Hauptmann Zimmermann shared his findings about the suspension and drivetrain systems. The vertical volute spring suspension was mechanically simple, almost crude by German standards, yet it appeared robust and designed for easy field maintenance. Each bogie assembly could be removed and replaced as a complete unit, requiring only basic tools and minimal specialized knowledge. German torsion bar suspensions offered superior ride quality and better armor protection, since they mounted inside the hull, but they required more complex installation and repair procedures. The Sherman's tracks used a simple rubber block design, less sophisticated than German track systems, but probably faster to manufacture and replace. What particularly caught Zimmermann's attention was the track's interchangeability. Each track link appeared identical, suggesting they could be replaced individually without concern for left-right or position-specific variations. This design philosophy prioritized field serviceability over optimal performance, a choice that seemed to characterize the entire vehicle. The second day of evaluation began with systematic dismantling procedures. Dr. Keller had prepared a detailed analysis plan overnight, identifying key systems for removal and examination. The workshop's large gantry crane had been positioned above the Sherman, its heavy chains and hooks ready to lift major components. 2 additional technicians had joined the team, experienced mechanics from the facility's vehicle maintenance section, who would assist with the physical labor of disassembly. The cold morning air inside Workshop 3 carried the smell of metal and machine oil as the team prepared their tools and equipment. Oberleutnant Bauer had been assigned to document the entire process photographically, creating a visual record that would accompany their written analysis. He had already exposed 3 rolls of film during the previous day's external examination and had requisitioned additional supplies from the facility's limited photographic stores. The first major task involved removing the Sherman's turret, a procedure that would reveal much about the tank's internal construction and design philosophy. In German tank designs, turret removal typically required disconnecting multiple systems, electrical connections for the gun's firing mechanism, hydraulic lines for traverse systems, ammunition feed mechanisms, and various instrumentation cables. The process demanded careful documentation to ensure proper reassembly and often required several hours, even for experienced technicians. The team approached the Sherman's turret with similar expectations, anticipating a complex disconnection process. What they discovered instead was remarkable in its simplicity. The turret sat on a large bearing race with a simple electrical connection for the turret traverse motor and basic mechanical linkages for gun elevation. There were no hydraulic systems, no complex cable harnesses requiring careful routing, no intricate ammunition feed mechanisms demanding precise alignment. The entire turret could be lifted free after disconnecting perhaps a dozen connection points, a procedure that took Zimmermann and the technicians less than 45 minutes to complete. The gantry crane's chains took the turret's weight, and slowly, steadily, the massive cast structure rose from the hull, swinging gently as it cleared the turret ring. The team guided it to a heavy steel support stand, where it could be examined in detail. With the turret removed, the Sherman's hull interior lay exposed to examination. Dr. Keller and Hauptmann Zimmermann descended into the crew compartment using portable work ladders, their work lights illuminating the interior space. What they found continued the pattern of purposeful simplicity evident in the turret removal process. The hull's interior was spacious compared to German tank designs, with generous clearances around major components. The driver's position, located in the left front of the hull, featured straightforward controls: a steering wheel, throttle, brake, and gear shift lever. No complex steering mechanism requiring skilled operation, no intricate control linkages demanding frequent adjustment. Everything suggested design for operation by minimally trained personnel. The transmission, visible in the forward hull section, appeared to be a straightforward 5-speed manual design, nothing sophisticated but robust and serviceable. Zimmermann examined the transmission's mounting points and access panels, noting how the entire assembly could be removed and replaced relatively easily. German tanks often integrated transmissions tightly with other hull components, making replacement a major undertaking requiring specialized facilities. This American design treated the transmission as a replaceable module, removable and installable with basic equipment. The hull's interior showed evidence of welded construction throughout. Unlike German tanks, where hull sections often featured complex interlocking joints and multiple types of fasteners, the Sherman's hull consisted of large plate sections welded together with continuous seams. Reinhardt, examining these welds from inside, confirmed his earlier observations. The welding quality was remarkably consistent, showing proper penetration and heat treatment throughout. The welds appeared to have been made using semi-automatic or fully automatic welding equipment, producing uniform results that would be difficult to achieve with manual welding processes. As the morning progressed, the team removed additional components: the engine's access covers, transmission inspection plates, and various smaller assemblies. Each removal revealed similar characteristics: simple attachment methods, generous tolerances, and design approaches that prioritized ease of assembly and maintenance over technical sophistication. The Sherman was beginning to reveal itself not as a sophisticated engineering achievement in the traditional German sense, but as something potentially more significant. A tank designed not primarily for superior battlefield performance, but for industrial mass production and logistical supportability at scales German manufacturing had never attempted. The afternoon brought the team to one of the most anticipated aspects of their analysis: the Sherman's power plant. Tank engines represented critical technology, and German engineers took considerable pride in their sophisticated Maybach designs that powered Panther and Tiger tanks. These engines featured advanced engineering, fuel injection systems, precise manufacturing tolerances, and complex cooling arrangements that delivered impressive power output relative to their displacement. Dr. Keller and Hauptmann Zimmermann prepared to remove the Sherman's engine, expecting a purpose-designed tank power plant similar to German practice. What they discovered instead was startling. The Sherman was powered by a Continental R975 radial aircraft engine, a design never intended for ground vehicle use, adapted for tank application through pragmatic engineering choices. The engine sat in the rear hull compartment, its distinctive radial configuration immediately apparent once the engine deck plates were removed. 9 cylinders arranged in a circle around a central crankshaft, air-cooled fins prominent on each cylinder barrel. This was not a sophisticated tank engine design emerging from years of specialized development, but rather an existing aircraft engine, proven in service, available in quantity, and adapted for a new purpose. Zimmermann found himself simultaneously impressed and troubled by this approach. From a pure engineering perspective, using an aircraft engine in a tank represented significant compromises. Aircraft engines prioritized power-to-weight ratios and were designed for relatively steady-state operation at consistent RPM. Tank engines required different characteristics, frequent speed changes, extended low-speed operation, and different cooling requirements. Yet here was an American tank using an aircraft engine, and intelligence reports suggested it performed adequately in combat operations. The implications were profound. Rather than spending years developing a specialized tank engine, American engineers had simply adapted an existing, proven design. This approach sacrificed optimal performance for rapid development and manufacturing leverage. The radial engine configuration also revealed something about American industrial capacity. These engines were being produced in enormous quantities for aircraft applications. By adapting them for tank use, American manufacturers could draw on existing production lines, existing supply chains, and existing technical expertise. No need to build new specialized facilities or develop new manufacturing processes. The infrastructure already existed, requiring only modification for ground vehicle installation. The team spent several hours examining the radial engine in detail. Zimmermann directed the removal process, with technicians disconnecting fuel lines, ignition systems, and engine mounting points. The Continental R975 displaced approximately 16 liters and produced around 400 horsepower, adequate power for the Sherman's 30-ton weight. German tank engines typically achieved similar power outputs from smaller displacements through higher compression ratios and more sophisticated engineering, but they also required more precise manufacturing and more careful maintenance. The American engine, while less efficient, tolerated rougher treatment and less precise service. Major Reinhardt examined the engine's construction, noting the relatively simple casting work compared to German engine blocks. The cylinders were separate castings bolted to a central crankcase, a modular approach that simplified manufacturing and repair. If a cylinder was damaged, it could be replaced individually rather than requiring replacement of an entire engine block. This modularity extended throughout the design. The magneto-ignition system, carburetor and cooling fan all attached as discrete, replaceable units. Everything about the engine's design suggested prioritization of maintainability and manufacturing simplicity over ultimate performance. As the radial engine was finally lifted clear of the hull using the gantry crane, Dr. Keller stood back, observing the suspended power plant with a mixture of professional interest and growing unease. The engine represented a fundamentally different approach to military equipment design, one that valued production capacity and logistical simplicity over technical sophistication. This American tank was not trying to be the best individual combat vehicle possible. It was trying to be a combat vehicle that could be produced in overwhelming quantities, maintained by minimally trained personnel, and supported by simplified supply chains. The engineering was adequate rather than exceptional, pragmatic rather than elegant. For a German engineer trained to pursue technical excellence, this philosophy was almost offensive. Yet standing in the cold workshop, surrounded by the Sherman's disassembled components, Keller found himself confronting an uncomfortable question. In industrial warfare, which approach would ultimately prevail? Superior individual vehicles produced in limited quantities, or adequate vehicles produced in overwhelming numbers? The third day of evaluation brought clearer skies but continued cold temperatures. Inside Workshop 3, the Sherman had been almost completely disassembled, its major components spread across the workshop floor in organized sections. The turret sat on its support stand. The hull rested on heavy wooden blocks with its suspension removed. The engine occupied a separate workbench, and countless smaller components lined additional tables in carefully catalogued arrangements. The scene resembled an automotive anatomy lesson, with each system exposed for detailed study. Dr. Keller had requested additional personnel for this phase of analysis, specialists in manufacturing processes and production engineering who could evaluate not just what the Sherman was, but how it was made. 2 civilians arrived from Berlin's Technical University. Professor Otto Steinmetz, an expert in industrial welding and fabrication processes, and Dr. Ludwig Hartmann, a specialist in casting technology and metallurgy. Both men had consulted for German armaments manufacturers and brought extensive knowledge of production engineering. Their task was to analyze the Sherman's construction methods and estimate the manufacturing processes, tooling requirements, and production rates these methods might enable. Professor Steinmetz began his examination with the hull's welded construction. He worked methodically, using magnification equipment to examine weld cross-sections, measuring bead widths and penetration depths, and studying the heat-affected zones around each weld. His findings, shared during a mid-morning briefing, painted a revealing picture. The hull's major welds showed characteristics consistent with submerged arc welding, a semi-automatic process where the welding arc operates beneath a blanket of granular flux. This process enabled much faster welding than traditional manual techniques and produced highly consistent results. More significantly, submerged arc welding required less skilled operators than manual welding. Where German tank production depended on master welders whose training took years, American production apparently utilized semi-automated processes that could be operated by workers with minimal training. Steinmetz estimated that the Sherman's hull could be welded in perhaps 1/10 the time required for comparable German tank construction using traditional methods. The implications for production rates were staggering. Dr. Hartmann's analysis of the cast turret provided equally revealing insights. The turret represented a massive single-piece casting, weighing approximately 2 tons, an impressive feat of foundry work. Hartmann examined the casting's internal structure, surface finish, and dimensional accuracy, comparing it against German casting capabilities. His assessment was sobering. The casting quality was good, but not exceptional by German standards. German foundries could produce superior castings with tighter tolerances and better surface finishes. However, producing a casting of this size and complexity required enormous industrial capacity, large foundry facilities, substantial energy input, and significant raw material throughput. More importantly, The turret's design reflected optimization for casting processes. Its rounded contours minimized sharp corners that could create stress concentrations or casting defects. Its relatively simple geometry avoided complex core work or difficult mold construction. The design sacrificed some ballistic efficiency. Angular shapes would have provided better armor effectiveness, but gained significant manufacturing advantages. The turret could be cast in existing foundries without requiring specialized tooling or extraordinary skill. It was a design optimized not for ultimate battlefield performance, but for industrial producibility. The team gathered around a large drafting table where Oberleutnant Bauer had prepared comparative drawings. On the left, a cross-section of the Sherman's cast turret. On the right, a comparable drawing of a Panther tank's turret, a complex assembly of interlocking rolled armor plates, requiring precise machining, careful fitting, and extensive welding. The Panther's turret was arguably superior in armor protection and internal arrangement, but it demanded far more manufacturing complexity. Bauer estimated that producing one Panther turret required perhaps 50 hours of labor across multiple specialized operations. The Sherman's cast turret, by contrast, probably required less than 20 hours from molten metal to finished product. When Professor Steinmetz added his estimates for hull construction time, a disturbing picture emerged. The complete Sherman could probably be manufactured in less than one-third the time required for a comparable German tank. Not because American manufacturing was necessarily more efficient in absolute terms, but because the Sherman's design had been optimized from the beginning for rapid production, using manufacturing processes that enabled less skilled labor and semi-automated operations. The fourth day brought a new focus: detailed examination of the Sherman's components, with specific attention to standardization, interchangeability, and maintenance characteristics. Hauptmann Zimmermann led this phase of analysis, drawing on his extensive experience with military vehicle maintenance and supply chain logistics. He had arranged the Sherman's removed components into functional groups: drivetrain elements, suspension components, electrical systems, and various hardware items. His team of mechanics began a systematic cataloging process, measuring every part, noting every fastener size, and documenting mounting methods and attachment points. By mid-morning, a pattern had emerged that was both impressive and deeply troubling to German engineering sensibilities. Zimmermann called the senior engineers together to share his preliminary findings. He had prepared a detailed chart listing fastener sizes used throughout the Sherman's construction. Of the approximately 800 individual bolts, nuts and screws used in the tank's assembly, only 11 different sizes appeared. 11. Dr. Keller absorbed this information with growing realization of its implications. A comparable German tank might use 25 or 30 different fastener sizes, often including specialized items unique to specific assemblies. The Sherman's radical standardization meant a maintenance crew needed to carry only a small set of tools to service virtually any component on the vehicle. It meant supply chains simplified dramatically, fewer unique parts to manufacture, stock, and distribute. It meant training became easier, since procedures learned on one system applied throughout the vehicle. Zimmermann expanded his presentation to other systems. The electrical components used standardized connectors throughout. The same connector type appeared on headlights, instruments, radio equipment, and various switches. Unlike German vehicles with their variety of proprietary connector designs, this American approach meant any connector could potentially be salvaged from a damaged vehicle to repair another. The tracks used completely interchangeable links. No left-right distinction, no position-specific variations. A crew could rebuild a damaged track using links salvaged from any other Sherman, mixing and matching without concern for compatibility. The afternoon session brought Oberleutnant Bauer's analysis of the suspension system components, and here the American standardization philosophy revealed itself most dramatically. The Sherman used a vertical volute spring suspension with 3 bogie assemblies per side. Bauer had completely disassembled one bogie unit and measured every component. What he discovered was remarkable. The bogie assemblies were entirely modular and completely interchangeable. Each assembly consisted of identical springs, identical wheel arms, identical wheel bearings and identical mounting hardware. There was no left-right distinction, no front-rear variation, no position-specific modifications. A crew could remove any bogie assembly and install it in any position on either side of the vehicle. More significantly, Bauer estimated that replacing a damaged bogie assembly would require perhaps 30 minutes of work by a two-man crew with basic tools. German tanks, with their more sophisticated torsion bar suspensions, required hours of specialized work to replace suspension components, often necessitating partial disassembly of hull sections. The American approach sacrificed some performance. The volute spring suspension provided a rougher ride than torsion bar systems, but gained enormous advantages in field maintainability. Zimmermann organized a practical demonstration of the implications. He had his maintenance team time how long it would take to replace several major components on the Sherman, using only basic tools, a socket wrench set, a few open-end wrenches, and a hammer. The results were striking. The transmission could be removed and replaced in under 4 hours, a complete bogie assembly in 30 minutes, the engine in 6 hours, a track section in 1 hour. Comparable operations on German tanks routinely required 2 to 3 times longer, often needed specialized tools, and sometimes demanded skills that only trained technicians possessed. The Sherman was revealing itself as a tank designed not primarily for the battlefield, but for the repair depot and supply warehouse. Its engineering prioritized keeping vehicles operational through quick repairs and simplified logistics rather than achieving ultimate performance. This represented a fundamental philosophical difference from German practice, where engineers pursued technical excellence even when it complicated production or maintenance.